Yeah, hello everyone. I hope that you can hear me.
Yes, we can.
Thank you very much again. I just want to be sure that you can hear me. Yeah, so today this lecture will be to formulate Gauss law. And as you remember, and as you will see, Gauss law allows to calculate electric field. But Gauss law allows to calculate electric field now quite easily if the charge distribution is very symmetrical, like spherical or cylindrical, or if the charge is on the plane. Because in the previous lectures and in tutorial today, we calculated electric field due to various continuous charge distributions, of course, using integral calculus. And sometimes these calculations can be quite lengthy and complicated. But as you will see, Gauss law allows to calculate electric field really very easily and very quickly, but under one condition, that the charge distribution must be very symmetrical. But before I explain Gauss law, first I have to define the flux of the electric field. And that concept of the flux, you probably remember from physics 1801, when we defined the flux of the magnetic field. And that was in relation to Faraday's law of electromagnetic induction. As you remember, if the flux of magnetic field through certain coil, let's say, change in time, then there is induced voltage in that coil. But here we will talk about the flux of the electric field. But the concept of the flux of electric field and magnetic field is very analogous. So imagine that we have here the electric field, and that electric field is represented by these vectors, by these arrows, and we have certain area represented by that green color. Maybe this is a square area. And as you see, that electric field passes through that green area. So we say that there is certain electric flux through that green area. So sometimes we use that term flux in relation to water flow. When water flows through a certain area, there is certain flux of water flows through that area. Of course, electric field doesn't flow, but it looks like these electric field lines now pass through that area. And the magnitude of that flux of electric field, as you might imagine, must depend on the strength of electric field, because when the electric field is very strong, then we represent that strong electric field by drawing now electric field lines of high density. We draw many of these electric field lines. So the more of these lines of electric field, the stronger is electric field. And then, of course, the flux of that electric field will be large if electric field is strong. But then that flux of electric field through this area will also depend on the size of the area. When the area is larger, then of course more of that electric field will pass through that larger area. So the flux of electric field should also depend on the area, but it also depends on the orientation of that area. So here you see, for example, when that area is at certain angle to the electric field. You see, in this situation, the area is perpendicular to electric field. Then a lot of electric field passes through the area. But when the area is now making certain angle, that like here is inclined to the electric field, then less of electric field passes through the area. And if the area would be parallel, to electric field, let's say like this, if this is the area and electric field would be like my pen, parallel, then of course no electric field would pass through the area. So clearly that the flux of electric field should depend on the angle between the area and electric field. So here's the summary of this, that electric flux, which we are going to represent by that capital letter phi, with subscript E, to remember this is the flux of the electric field, is really given by this product of the strength of electric field. The stronger electric field, the bigger the flux. On the area, the bigger the area, the more electric field. But also depends, the flux depends also on this angle between the area and the electric field, and that angle I designated by letter theta. but that angle is defined in slightly unusual way. It's actually, which is explained on that side on the screen, that if we have certain area and electric field this time is represented by these dotted lines, then the angle is, you see, the angle between the area vector, and the area vector was defined in physics 1801, but remember the area vector is the vector which has magnitude. Remember, vector has to have magnitude and direction. So the magnitude of area vector is equal to the area, which is in meters squared, maybe 2 meters squared. And the direction by definition is perpendicular to the area. So you see, so this, if this is the line in that area, then this is 90 degrees. So area vector is perpendicular to the area. That's the definition of the area vector. And then this angle theta is the angle between the electric field and that area vector. So then, now knowing the definition of the area vector, this product EA cosine theta can be written as the dot product, E dot A, right? Because dot product involves cosine function. But remember, the angle is between the area vector and electric field. So this is how we define the flux of electric field through open surface, like this square surface or any open surface like this. And you should also see that we can decompose that electric field into electric component which is parallel to area vector. That would be that component E, parallel to the area vector, parallel, and component of electric field which is perpendicular to area vector, which means the component which is in that plane. This is that component E perpendicular to area vector. So as you see, only that component of electric field parallel to electric field will contribute to the flux of electric field. And this component, which is parallel to the surface, of course, doesn't pass through the surface. So this component perpendicular will not contribute to the flux. So we sometimes say that yeah, only that component of electric field parallel or perpendicular to the surface contributes to the flux of electric field. So any questions so far about the definition of the flux of the electric field? So as you see, this is the same definition as now for the flux of the magnetic field. It is the same type of concept. So that hopefully is all clear for you. But in the Gauss law, we will talk not about the flux through this open surface, like that flat surface, but in the Gauss law, we will be calculating the flux of electric field through the closed surface. So here you have now visualization of that concept, that we have a certain closed surface, like certain balloon, and that surface, that closed surface, is located in electric field represented by these black lines. And as you see, some of that electric field will enter that closed surface, and some of the electric field will leave the surface. And we will be calculating the net flux of the electric field through that closed surface. So how would you then calculate the flux of electric field through that closed surface? Well, the only solution would be to do the following, that we would have to divide that surface, that closed surface, into many tiny rectangular areas, and each, so you see this, many of these rectangular areas, and each of these tiny rectangular areas is designated here now as delta E. So that would be like differential area, dA. So that surface area should be so small that it should approach, dA should approach 0, right? It should be very tiny. And if it is very tiny, then we can treat each of these little tiny surfaces as flat, because it's so tiny that we can treat it as flat. And then we can calculate flux of the electric field through each tiny area. And this is that flux through each tiny area. And then we would have to find the sum of the flux through all tiny areas on that surface. and we should find that sum under the condition when delta A approaches 0, which means that if we calculate a limit of that sum under the condition when delta A, each of these tiny areas approach 0, then that's how you would calculate the flux through that closed surface, right? And that limit of that sum, as you know from calculus, that limit of the sum is nothing else but definite integral of that E dA. So this is that integral E dA. But that little circle on integral means that we would have to calculate that integral over the closed surface, So we should remember to write that circle here. So this very often we call a vector surface integral, because you see what we integrate over the electric field, and the electric field is a vector quantity. So here we have dot product, E dot dA. So these are particularly difficult to calculate, because if that function under the integral, if that integrand is a scalar function, you can calculate the surface integral of the scalar function. But here we have to integrate over the surface of the vector quantity. And as you see from this visualization, the magnitude of electric field at every point on the surface, on every point of that closed surface will have different magnitude and different direction. So we have to take into account the dot product. What is the magnitude of electric field and what is the angle of electric field at that particular point on the surface with that area vector dA. So these are complicated integrals to evaluate. So what we have to do is slightly better visualize also with the three examples, that at every little area of that surface, at every point is area, and three are now designated A, B, and C. So for example, for this, let I start with C. So for this surface area, tiny surface area, the electric field might be, and this is enlarged here. So this is the little area dA, and let's say a vector E at that point on that surface is in this direction, and area vector, which is perpendicular to the surface area, maybe in this direction. So this angle here would be probably smaller than 90, and the flux through this little area would be positive, right? Because cosine of the angle less than 90 is positive, so the flux would be positive. But if you take, let's say this little surface area, this one at A, then here the electric field at that location would be maybe in this direction, but the vector area which is by the way perpendicular to area, would be in this direction, and this angle is now bigger than 90 degrees, and cosine of the angle more than 90 is negative. So you see the flux through this little surface would be negative, because this angle, cosine of this angle, is negative value. And that will be always the case, that whenever the flux flows into the surface, it would be negative, and the flux of the electric field, when it leaves the surface, will be positive, okay? Because then the angle would be here less than 90, and when it flows into, this angle will be bigger than 90. So the flux can be positive and negative. As I'm saying, whatever flows into the surface will be negative, whatever of electric field flows out of the surface will be taken as positive. And for this area B, you see, this area B is such that no electric field at this point on the surface is maybe in this direction, and area vector would be more or less perpendicular to it. So the flux through this area would be 0, because here electric field would just pass parallel to that surface. So at this point now, the flux through this little area would be 0. So as I'm saying, to calculate the flux of electric field through the closed surface, we have to evaluate that vector integral over the closed surface. So that's pretty complicated how to do it. But as you will see in a minute, in most cases, that surface area which we are going to use will be either spherical or cylindrical, something like that. And then calculations are much, much easier. But in general, that could be complicated. And in calculus, you will be learning how to evaluate the surface integral for the scalar function or for vector quantities. So that will be part done in calculus. So any questions about that slide for now? One thing which is extremely important, which I should emphasize very strongly, is that by definition, that area vector delta A for each of these tiny surfaces, by definition, delta A is directed to the outside of the closed surface, to the outside. You see, so at this point, area vector A is in this direction. For this surface, in this direction, to the outside, to the outside, always to the outside. That's the definition of vector delta A for the closed surface. Any questions?
Professor, I have a question. Could you please explain the last sentence? Only the component of the electric field perpendicular to the surface contribute to the flux. Why is that?
Yeah, actually, that's a very important question. That, to explain this slightly better, I'm going to return to the previous slide where I probably explained that a little bit too fast. So on that slide, so imagine that we have here the flat surface in the electric field. Dotted lines are electric field. So if that area vector makes certain angle with electric field, right? That angle is here theta. Then you see that electric field I can decompose into electric field parallel to area vector, right? Like I designated this again as E parallel, because remember, vector E can be decomposed into two components. So I decompose it into component parallel to vector A and component perpendicular to vector A, you see? So this here I decompose vector E into two components. This is E perpendicular to the so this angle is 90, and this component is parallel. So you see this component, which is perpendicular, this component doesn't pass through the surface because it just glides parallel to the surface. So, but this parallel component of the electric field passes through the surface. So, so that's the meaning of that statement which you ask about on the next slide, that when electric field makes certain angle with area A, then actually only that component of electric field parallel to the surface, parallel to that area vector, which means that component of electric field perpendicular to the surface must be taken into account, because that component parallel to the surface or perpendicular to area vector does not contribute to the flux. So that is the statement which I have written on the next slide. And that was your question about this statement, that only components of electric field that are parallel to the vector area would contribute to the flux, right? So that is this. Also, I have rewritten this also on the next slide. So that was the same statement here, you see, on that slide. On that, only components of electric field perpendicular to the surface, which means parallel to the area vector, contribute to the flux.
Okay, got it. Thank you.
Yeah, thank you very much. Good. So, any additional questions? So, if not, let us quickly calculate what is the flux of the electric field for this situation. When electric field here, represented by these black lines, is uniform in space. So you see these electric field lines are parallel to each other. And we want to calculate the flux of the electric field through the cylindrical surface, which is a closed surface, right? And that cylindrical surface has, these two ends are circular surfaces. And that side surface is that cylindrical surface, so there are three parts of that surface. And so in this case, because electric field is uniform, to calculate electric field, I can calculate the flux first, maybe through this surface, which is circular surface. Then I will calculate flux through this surface. And then I calculate the flux also through that side, through that cylindrical surface, okay? So let us calculate what is the flux of the electric field through this circular surface. So because at any point on that circle, electric field has the same magnitude and the same direction because electric field is uniform. So at every point within that circle, at this point, at this point, at this point, at this point, at any point, electric field has the same magnitude. So the flux through that surface would be equal the area of that circle, which is pi r squared, times the magnitude of the electric field, which is a uniform electric field of magnitude E. So you see, so this is the contribution, this contribution, which is the last term actually, because here the area vector is perpendicular to this circle, is parallel to electric field. So the angle would be 0 degrees. So here we have, I have to multiply electric field in that circular area times the area, which is pi r squared, times cosine 0, because electric field here is parallel to the area vector. So this is the contribution to the flux to this area, which would be equal of cosine of 0 is 1. So it would be e pi r squared, so which is this term. Now let us calculate flux through this surface, through this circle. Well, here the area vector is, remember, always to the outside of that closed surface. So here the area vector would be in this direction, which is anti-parallel to electric field. You see, electric field is to the right, but area vector here is to the left. So the angle theta between electric field and area vector is 180 degrees. And because electric field, again, is uniform everywhere within that circle is of the same magnitude, so then I multiply electric field times the area times the cosine of 180. Cosine of 180 is -1. So the contribution to the flux through this surface would be equal negative E times pi r squared. And I still have to calculate the flux through that side surface of the cylinder. But here you see, no matter which element of the surface I take, of the cylindrical surface, that area would be always to the outside and perpendicular to that area, you see? So no matter which element of that surface I take, vector dA will be perpendicular to electric field because electric field is, you see, horizontal. So at any point on that surface, no matter which element you would take, area vector delta dE will be to the outside, and it will be perpendicular to electric field, perpendicular. So the contribution of that side surface to the flux, we calculate like this. Take the electric field, and again, electric field is uniform in space. So at this point, at every point on that cylinder, electric field is the same magnitude and the same direction. So I have to multiply that electric field times the area, this now area, and the area of that side surface is equal 2 pi r L. So if the radius of the cylinder is r, if this is r, then as you know, if you have a cylinder, so please look, because I will be using this. So if this is my cylinder, this is that side surface, this is the radius, right? This is the circle, this is the radius. When I unwind that surface, what do I get? I get a rectangular area for which this side of the rectangular area is 2 pi r equal to circumference of the circle. No, so this one, no, sorry. So I made like this. So this is again my cylinder. This is radius r. When I unwind it, then this side would be 2 pi r. This would be 2 pi r circumference. And this is the length of my cylinder, length L. So that side surface is really, as you see, a rectangular area. And one side of the rectangle is 2 pi r, and the other side length of the cylinder. So this is L. This is L. This is L. Capital L. So 2 pi r times L is the area. So I multiply electric field, which is the same at every point on that surface, times 2 pi r times cosine 90, because the angle between electric field and any area vector of that surface is 90 degrees. And cosine of 90 is 0. So that's this contribution. So as you see, the total flux of the electric field through that cylinder is equal to 0, because this area contributes to negative flux, that gives negative flux, this gives a positive flux, and that side surface does not contribute at all, because electric field is just parallel to that surface. So you see, so here electric field through this area, through this circle, it enters the cylinder, and that flux is negative, and here electric field is leaving the cylinder, and that flux is positive. See, so here this flux is negative because electric field enters the cylinder. This is positive because here electric field is exiting the cylinder, and the side surface contribution is 0. So the total flux is equal to 0. And that will be always the case. Whenever, whatever, no matter what is the shape of the surface. So it could be a balloon of any shape, as long as you put that surface area in a uniform electric field, the total flux through that closed surface will be 0 in a uniform electric field. You will see. Okay. So yes, please.
Okay, so so this is a uniform electric field. The electric field strength at point A is the same as at point C. Yes,
and at point B, at every point, the electric field has the same magnitude because it's a uniform in space electric field. That's very correct. And
Sorry,
only
I have a quick question.
Yes.
Are we ever going to do non-uniform electric fields?
We will actually, we will probably not.
Okay.
Although maybe I will, so we'll see. But in most cases, as you will see, the electric field within certain areas. So we will have non-uniform electric field. But when we calculate flux through certain closed areas, the surface will be such that we will be able to divide the surface into parts. And in each part of the surface, like in this case of that cylinder, electric field will be uniform within each part. So the electric field will be non-uniform, but when we calculate the flux through certain areas, the electric field within that area will be of the same magnitude everywhere, because only then these integrals are very simple to evaluate. So you see, so in this case, for that cylinder, I did not really do any integration. Why? I didn't have to do integration. It was not needed because electric field within this circle, at any point within this electric field has the same magnitude in the same direction. Within this circle, electric field was the same, uniform, and within the side surface, electric field everywhere had the same magnitude, although different directions. So electric and direction and magnitude was the same. So that was particularly simple. But as you will see in the future, electric field will be non-uniform, but we will be still able to do flux calculation very, very easily.
Okay, thank you.
Very, very easily. Okay, so good questions.
I have one more question.
Yes, please. Okay, go ahead.
All right, so you said that for the area vector, it always goes out of the surface.
Yes.
Does that mean that there's no field within the surface?
No, there is field, you see, because we have to calculate flux of the electric field through the surface. And to do that over the surface, so we have to always take what is electric field at every point on that surface, not inside of the surface, but on the surface of that surface. So you see, I'm only dealing with electric field, which is at every point on that cylindrical surface, not inside. You see, there is some electric field inside, but when you calculate the flux, you have to take electric field at every point on that surface.
All right.
Remember, like, it's a very good question. It's actually a source of confusion for many students. So if I go back to this definition of the flux, remember, we divided that surface into tiny rectangular areas, and we calculate the flux through little area. And to do it, I had to take electric field at that particular point of that area. What is electric field at that point on the surface? When I took this little surface, then I had to know electric field at that point on the surface. Or when I took this, I had to take electric field at that point on the surface. So in flux calculation, what comes into play is electric field at every point on the surface. Every point on the surface. Because this is called surface integral. Right? So this electric field we take at dot product at every point on the surface. So I'm glad that you asked that question, because it's a source of confusion for many students, actually, the meaning of that surface integral. So yeah, so you will get a handle of it now very quickly once we do more examples. Okay, so let us do this. Yes, please.
Sir, so just to confirm, so like as long as the surface is closed, the flux is always going to be 0.
But only if that surface is in a uniform electric field.
In a uniform, so
yeah.
So like
if the field would be non-uniform, as you will see, we will get to this question again. But you will see the following. Okay, so the essence of the Gauss law will be the following: that if you calculate the flux through certain closed surface, and if that flux is not equal to 0, then that will indicate to you that there must be some charge inside of that surface. There must be some charge inside of the surface. But in this case, which I was considering here, there is no charge inside of that surface. So the flux, if there is no charge inside of the surface, the flux through the surface will always be equal to 0, whether the electric field is uniform or not uniform. The only reason for the flux of electric field to be not equal to 0 is if there is a charge, net charge. There might be some positive, some negative charges, but if the net charge inside of the surface is not 0, if there is some charge inside, then the flux through that surface will not be equal to 0. So I will formulate the Gauss law in a minute, but as I've mentioned before, no matter what surface I would put, no matter what shape of that surface would be in that uniform electric field, no matter what the shape of that surface, if the charge inside of the surface is 0, the flux will be through the surface will be 0, whether field is uniform or not uniform.
So like, will we be dealing with open surfaces in this class?
No, in Gauss law, we always will deal with closed surfaces.
Closed surfaces, okay.
Yeah,
okay.
Like in Faraday's law for magnetic flux, we did deal with open surfaces. But here we deal with closed surface, as you see. I still have not formulated the Gauss law, but you ask good questions. So I go a little bit ahead. But on this slide, I wanted to formulate the Gauss law. Okay, so this example, which we are going to do right now, will help me to formulate that important Gauss law. But that Gauss law will be really the conclusion of the following example. So in this example, let us calculate the flux of the electric field through a spherical surface which surrounds a point charge located at the center of the surface. Okay, so please listen carefully. So the situation in this example is this, that I have certain charge Q, positive in this case, and that positive charge produces electric field. Remember that electric field due to that positive charge is going radially away from that positive charge, right? In all directions, electric field lines are radially away from that positive charge. So that charge is the source of electric field, right? That charge is the source of electric field. And I want to calculate now, what is the flux of that electric field produced by that point charge? What is the flux through the spherical surface which surrounds that point charge. So that surface is a sphere around. Okay, so this is not a disk. This is a sphere or around that charge. And I want to calculate what is the net flux through that spherical surface surrounding that charge. And the charge is located now at the center of the sphere for now. So look, you should first observe that the electric field at any point of the surface, you see, is perpendicular to the locally perpendicular to the surface, because that electric field is along the radial directions everywhere, you see. So no matter what little area you take of the surface, at that point, electric field is perpendicular. This is 90 degrees, perpendicular to the surface. So this is indicated here that no matter what little area of that surface, of that spherical surface I take, the area vector, which by definition is to the outside of the surface, that area vector dA will be parallel to the electric field produced by that charge. Do you agree with me? No matter what I take that little area, the area vector dA will be along the radius, and electric field is also along the radius at that particular point. You see, at every point of the surface, dA will be parallel to electric field at that point on the surface. Do you see that? Do you all agree that at any point of the surface, dA and E will be parallel? Because remember, electric field is radially away, so electric field is along the radius of the sphere, and the area vector is perpendicular to the sphere. So dA must be parallel to electric field. So if you take this into account, then the flux, which is equal to that, integral over the closed surface over that spherical surface, E dA. So that would be, so the dot product is E dA cosine theta, but cosine theta is 0 because dA and E are parallel. So angle theta is equal to 0, right? Equal to 0. And because electric field, so please listen carefully, because my charge is at the center of the sphere, then an electric field produced by the point charge is given by this expression, is equal, remember that constant K, which I'm going to write as 4 pi epsilon 0, right? That Coulomb constant, 4 pi epsilon 0, Q epsilon 0, it's difficult for me to write with my mouse, Q divided by R squared. So as you see, electric field due to point charge depends only on the distance. And you see any point on the surface of the sphere is always at the same distance, R, from that charge, which is inside of that sphere, at the center of the sphere. So, so as you see, the electric field has a constant magnitude at every point on the surface of the sphere, because electric field depends only on the distance in terms of magnitude, right? Electric field in terms of the direction is radially away, but in terms of magnitude depends only on the distance from the point charge, and every point of the sphere is the same distance r from the center of the sphere. So electric field has the same magnitude at every point on this spherical surface. So because electric field has the constant magnitude, I took it in front of the integral, because electric field is constant on that surface of the sphere, constant in magnitude, and cosine of 0 because dA is always parallel to electric field at every point on the sphere. So I took this also out, and I have to integrate over the sphere dA. And what is the integral dA? What is the area of the sphere, which is 4 pi r squared. So you have to now memorize that formula, which I know because my children went through elementary school and high school and university. So I know that in elementary school, in grade 7 or 8, they explained that area of the sphere, surface of the sphere is 4 pi r squared. So you should remember that value, right? Area of the circle is pi r squared, but the area of the spherical surface is 4 pi r squared. So here you see, so I substituted now for electric field, the electric field due to the point charge, which is Q divided by 4 pi epsilon 0 r squared, and the area is 4 pi r squared, and as you see, r squared will cancel, and the total flux is equal Q, and 4 pi will cancel, and the total flux is equal Q divided by epsilon 0. So in this particular case, what we have proven is that the total flux through that spherical surface is equal to the charge Q, which is located inside of the spherical surface, divided by epsilon 0. So for that specific example, which I did, we have proven that the flux of electric field is equal charge inside of that spherical surface divided by epsilon 0. So I did that derivation, and this is called the Gauss law, that the Gauss law tells you that the flux through any surface, no matter what is the shape of the surface, is equal to the charge inside of that surface, net total charge inside, divided by epsilon 0. This is the general formulation of the Gauss law. So please listen carefully a little bit more. So you see, my derivation of the Gauss law was for that specific case when the charge Q was at the center of that sphere. But even if the charge Q is not at the center, if that charge Q would be somewhere here, closer to, not at the center, it is still possible to prove that the total flux through that surface is still equal Q divided by epsilon 0. Although you see, if the charge is not at the center, that electric field maybe at this point, on the surface, close to that charge here, electric field would be strong, and maybe here at this point far away, at this point on the surface, far away from the charge, electric field would be weaker. But it is still possible to prove that the total flux of the electric field produced by that charge would be still equal Q inside divided by epsilon 0. So no matter at which point that charge is located inside of the sphere, the total flux will be always equal Q inside divided by epsilon 0. Or you might have maybe a few charges at different locations. Maybe some charges can be positive. Some charges inside of the sphere might be negative. If you calculate the net charge inside of that sphere, that Q inside would be the net charge. So some positive and some negative would cancel each other. But if you take the net charge inside of the sphere and divide by epsilon 0, that will be equal to the total flux through that surface. In addition, I can tell you even more, that Gauss law is even more general, that if I would not have that surface to be spherical, but let's say if I replace that spherical surface by any type of surface, no matter how complicated in shape, the Gauss law tells you that the total flux through that surface, no matter how complicated is that surface, remember that surface must be a closed surface, that the total flux is always equal to the net charge inside of that surface. So the Gauss law is extremely important, and useful, and so this is the general formulation of the Gauss law. And remember that the surface does not have to be spherical; it can be of any shape. It has to be closed surface, and charge Q can be positive or negative. Could be many charges, whatever. The total flux produced by these charges through that surface of any shape is always equal Q, the net charge inside divided by epsilon 0. So the general proof of the Gauss law is complicated, and we will not do it. I just wanted to show you that for that particular case, we did derive sort of that Gauss law. So what is the significance of Gauss law? You see, the significance of Gauss law is this, that, please listen, the significance is that the surface can be very complicated. The electric field, so the surface can be very, very complicated in shape, can be three-dimensional closed surface. Electric field at any point on that surface might have different magnitude and different direction, so that the flux of that electric field can be horribly difficult to calculate. But the Gauss law tells you that no matter what is the surface, no matter what is electric field on that surface, the flux must be equal to simply the net charge inside divided by epsilon zero. So you see, instead of calculating complicated surface integral, you can just replace that complicated surface integral by that result, Q inside the net charge inside divided by epsilon zero. That's what Gauss law tells you. And that's why it's so very powerful and important. So I did use many, many words, and I am not sure if you understood my explanation, but that is the meaning of the Gauss law. That's the significance of it, that the flux through any closed surface must be equal to the charge, net charge inside, because I repeat again and again, that charge inside can be, some charges can be positive, some negative. You always have to calculate the net charge, the total charge inside. So any questions right now regarding Gauss law? You must be overwhelmed by its significance, probably. So any questions? So if you don't have any questions, we will do now a few examples. And you will see how the Gauss law can be used to calculate actually electric field.
Hi, Professor. Sorry
yes.
to butt in. Just
go
to
ahead.
clarify then,
Yes.
I was wondering, so the total surface charge is equal to the flux?
I didn't use the total surface charge. So the term which I use here, you see this Q inside, I wrote that Q inside because that charge is inside of that surface. It's not on the surface, it is inside of that surface. Like here, you see that charge Q is at the center of the sphere, and that surface is that surface of the sphere surrounding that charge. So Q inside is the charge inside of the surface, but electric field here in this expression, that electric field is electric field on every point on that surface. So this electric field is the field at points on the surface, but Q is the charge inside of that surface.
And that's equal to the flux.
And yes, and that Gauss law tells you that no matter what is the shape of that surface, no matter how complicated it is, the total flux of electric field through that surface must be equal to the net charge inside of the surface, and you have to divide this charge by epsilon zero. That's what Gauss law tells you. So it's actually extremely, Gauss was a genius, as you know. I told you that before, that he is called Prince of Mathematics, and he was actually, at the age of 2, he did calculations which people could not do when they were very old. It's actually, you could read the story about Gauss and other geniuses. It's amazing to read about them. Anyway, so he has proven this in general term. I will not do it because
all right, thank you.
You will use Gauss law in your multivariable calculus probably, but I'm explaining just physics of it. Okay. So good questions, and you will get the handle of Gauss law when we do few more examples, because you see, from maybe I should make this one comment a little bit again, that from theoretical point of view, like for theoretical physicists or mathematicians, the Gauss law, you see, allows you to replace that complicated integral. And that integral can be horribly complicated because this is a vector integral over the surface. So the surface can be complicated. Electric field might be not uniform, different in magnitude and direction at every point on the surface. So this integral could be horribly complicated. But the Gauss law tells you that you can replace that complicated integral by that simple expression, charge inside divided by epsilon zero. That's the amazing part of the Gauss law. But in practice, what we are going to do in this course, we will use Gauss law to calculate, given that charge inside, that will allow us to calculate electric field. And that, so we will use Gauss law actually to calculate electric field, and that will be only easy if the surface which we select is very symmetrical, like spherical or cylindrical, something like that. And you will see how we will use Gauss law to calculate electric field through a number of examples. And the first example I would like to do right now, and I know that the time is running very quickly, but we will be able to do it very quickly. Okay, so look, please concentrate still a little bit more. So we will now use Gauss law to calculate electric field produced by infinitely long line of charge. Do you remember previously, in previous lectures, we calculated electric field due to infinitely long line of charge. We did a lot of integration, and final result, which we've obtained, was of that type, of that type. So that was the result of all that integration. But this time, we will use Gauss law to calculate electric field due to infinity long line of charge, and it will take just 2 lines to get the same result. So instead of pages of calculations, you just write 2 lines and you get the same result. So let us do the calculations. So according to Gauss law, if I have infinitely long line of charge, then previously we concluded that the electric field due to the line of charge is always radially away. These green vectors represent electric field. But even if we would not have done these calculations previously, you would have to conclude that if the charge is uniformly distributed on the line of charge, electric field must be radially away from it, because it would not make any sense. Any other direction of electric field would not make any sense. And I could show you why it would not make any sense, but due to the symmetry of the charge distribution, electric field must be radially away from that line of charge. So if you accept that fact that electric field is radially away from that positive line of charge, then let us use Gauss law to calculate the electric field. So to use Gauss law, we are going to surround that line of charge by cylindrical surface. This is visualized here. So this is the line of charge on infinitely long line of charge. We will surround it by cylindrical surface. And you will understand in a minute why cylindrical surface is the most convenient. So this line of charge is now surrounded by cylindrical surface, so that that line of charge goes through the center of the cylinder. And we now calculate the flux of the electric field through that cylindrical surface, right? So we will use that field produced by that line of charge, and it should declare the following, that the flux we can calculate through each surface separately. So we will calculate flux of the electric field through this circular surface. Then we calculate flux through this circular surface and through that side surface, so that the total flux will be split into the 3 parts, right? So the total flux through that closed cylindrical surface, we can split into flux through this circle, and cylindrical surface. Now, but it should be clear to you that because for that circular surface, the area vector dA by definition is perpendicular to that circle and in the direction away from that closed surface. But electric field due to line of charge is radially away from the line of charge. So electric field makes 90 degrees with the area vector of that surface, of that circular surface. And because cosine of 90 is 0, then this electric field does not pass through this circular surface. The same argument I can use for that surface, you see? Because here, again, this is a circular surface, and electric field produced by the line of charge will be parallel to the surface, so that electric field will not pass through this circular surface. But electric field will pass only through that cylindrical surface. And at any point of that cylinder, the area vector dA is parallel to the electric field, which is again radially away from that line of charge. So you see that integral, which is the flux through that cylindrical surface, is equal only electric field on that surface of the cylinder, on that side surface of the cylinder, which is E, which we don't know. But at any point on that surface, electric field would have to be the same magnitude, because any point on that surface is the same distance from the line of charge. So electric field will be constant times the side surface, which is 2 pi RL, right? Because the radius of the cylindrical surface I took to be R, so 2 pi RL. And cosine of 0, I should write cosine of 0, cosine of 0. Okay, so the total flux of the electric field through the cylindrical surface must be equal E 2 pi RL cosine of 0. Cosine of 0 is 0. And that total flux, which is E times 2 pi RL, must be equal to the net charge inside of that surface divided by epsilon 0. And how much charge is inside of the spherical surface? We can find if we assume that lambda surface charge density is given. If lambda is given, then charge Q inside, and remember that lambda is equal the charge divided by length. So if the length of that cylindrical surface is L, then amount of charge inside of the surface would be equal just Q L times L, lambda, L times lambda. That would be the net charge inside of the cylindrical surface, right? Do you agree with me? So the Q inside is lambda times L. So the total flux is E 2 pi RL. The total charge is lambda times L divided by epsilon 0. We can solve this equation for E, and the result is 1 divided by 2 pi epsilon 0 lambda times R, which is the same which we've obtained doing calculations previously in previous lectures. So I did go through this example relatively fast, and I'm pretty sure that it's probably too fast for many of you, but if you did understand then you are geniuses, then you are very bright people. But if you did not understand, then I will repeat this example again in the next lecture. But because I still have a little bit of time, I can answer your questions for now, if you have any questions right now.
Hello, sir.
Yes.
Wait, am I allowed to ask questions that's not related to the topics that you took today?
Okay.
So when I was trying to solve questions that, for example, you wrote an assignment for chapter 25 to 25.1 to 25.5, and I went through the book, I had troubles finding, like, for example, you wrote problem 1 and problem 3 is suggested to solve. Like, are these questions at the end of chapter 25, or is it like examples throughout each section?
Well, so these questions which I specified on E-class for each chapter, which I sort of treat like honor assignments, right? You don't have to submit assignments, but I suggest that you should be able to do them.
Yeah, I know. I just had trouble finding them, not solving them. Like, I wasn't able to find which questions you meant for us to solve.
So they are specified on E-class. So when you go to E-class, I have made a list of paragraphs. And then I also written EX exercises, let's say 5 or 15 or 16. There is a list of these questions on E-class for each chapter.
Okay.
Yeah, and you should try to do them.
Okay. And just one last question. Yes. For the sample test that you posted in CrowdMark, that's not for marks, right? It's just for us to practice?
Yes, that's just for practice, yes.
Okay, and like...
But for that CrowdMark, there is only one question on that sample test on CrowdMark, which is posted. And the solution of it is in tutorial notes and in the lecture notes, actually both. And so even if you don't do it correctly, although solution is posted, you should submit, because I just need proof that you know how to submit solutions on CrowdMark. That's the purpose of that sample test. Okay, because I don't want to be faced like in previous semesters that many students then send me, sir, I don't have access to CrowdMark. They write the test and they don't have access to CrowdMark. That should not happen again in this course. Okay, so this is the role of the sample test. Make sure that you know how to submit, because if you don't submit questions on CrowdMark on October 4th, you will get 0.
Yeah, of course.
Okay.
Okay.
So that's the. So I will redo this question again at the beginning of the lecture on Friday. And maybe in the meantime, you should spend a little bit of time at home to redo this question, which you see on the screen right now. At home, think a little bit about this, read the textbook, the same is done in the textbook, and see how I use the Gauss law to calculate electric field due to infinitely long line of charge. And that took only 2 lines. And previously we took few pages to do this question to get the same result. So Gauss law is very useful, but only if the charge is distributed symmetrically, like on the line of charge. So any questions?
Sir, can you go over again where you got the 2 pi RL?
Yeah, I will do it again, but yeah, I will do it again. So how I got 2 pi RL, because you see, when I calculate the flux through that closed cylindrical surface, you see, this is the cylindrical surface, right? That surface has 3 parts: this circle, and that side surface. But that side surface is, you see, this is my model of the cylinder. See, so here it is, the cylinder, right? Do you see the cylinder? And the line of charge is like lying like my pen inside of the cylinder. See, like this. Now, when I calculate the flux through this surface, you see, when you are, so this is the radius of that cylinder. When I unwind it, then I get a rectangular area. And this side is 2 pi r, and this side is the length of the cylinder. And the area of that surface is 2 pi r times L. So here is this, that the flux through that side surface is the electric field on that surface, which I called E, times the area, 2 pi r, times cosine of 0, right? Because the dot product involves cosine of 0. Because at any point on that side surface, electric field is parallel to area vector, so the angle is 0, cosine of 0 is 1. So the entire flux through the entire surface area is 2 pi r L times E times cosine 0, because there is no flux through this circular surface part of the cylinder or through this one, because here electric field is perpendicular to area vector delta A. So E times delta A cosine 90 is 0. So only the flux is only through that cylindrical surface, side surface, for which area is 2 pi r times L. So that's a very good question. So please try to think about my explanations at home today, and I will do this question again on Friday. But for now, I will stop recording.